Okay, so here's our Exam 2 prep, College Algebra, Kingwood. I'm being shown the presenter view, which, okay, looks different than I'm used to. Okay, so here we go. Okay, so here we are given a rational function, a rational or fractional function. It says find the vertical asymptotes. And that is the very first thing that we want to do, is find, if the problem on the exam is find all asymptotes, it's really three problems. First, you want to find vertical asymptotes. Secondly, horizontal, and then there really should be complete partition between that problem and the third problem, which is to find a slant or oblique asymptote. To find a vertical asymptote, the thing about it is that the rational function has to be in lowest terms. And you don't really know that until you factor it, top and bottom. The top actually is a prime binomial, so it can't be factored. It is a factor, okay? So it's kind of like it is a factor. You could have the whole thing in parentheses. In the bottom, we've got a difference of squares, which factors to the product of conjugates, x plus 4, x minus 4. And the zeros of the denominator always give you the vertical asymptotes if you have lowest terms, if you have simplified form, okay, with all possible canceling done, okay? So reduced form, big deal there. Then once you have that, then it's okay to get the zeros of the denominator. So we're going to set the denominator x plus 4, x minus 4 equal to 0. And if you have two things that multiply together to make 0, one of them has to be 0. Either the first thing, that's a parenthesis right there, either the first thing equals 0 or the second thing equals 0. Subtract 4 from both sides, x equals negative 4. Or add 4 to both sides, x equals 4. Now those are solutions to the equation. Those are zeros of the denominator. But those equations are actually equations of the graphs of which are vertical lines. And those vertical lines are the vertical asymptotes. What's an asymptote? An asymptote is a line that a curve approaches. And so those are the two vertical lines that this curve will approach. Okay. Now let's talk about a horizontal line that the curve approaches. In other words, a horizontal asymptote. Now, remember how Miller gives us a very good, easy three-step or three-case approach to horizontal asymptote. In each of the cases, you can do the problem mentally. Okay? You never really have to write anything. to find the equation of a horizontal asymptote if one exists. Okay, and basically it has to do with the degree of the top and the degree of the bottom. In this case, degree of the top is 2, right? Because that's the highest power on x. Degree of the top is 2. The degree of the bottom is also 2. That's the highest power on x in the denominator. Okay? So 2 is the degree of the top. 2 is also the degree of the bottom. And if the degree of the top equals the degree of the bottom, then the horizontal asymptote well, it's a horizontal line, so as all horizontal lines do, it'll have an equation of the form y equals a number. And that number is the ratio of the lead coefficients. In this case, the coefficients on x squared for both terms. So the lead coefficients are 2 in the top and 1 in the bottom. 2 in the top, 1 in the bottom. So the equation of the horizontal asymptote is y equals 2 over 1, or it's the line y equals 2. The horizontal line 2 units above the x-axis. Y equals 2 is the answer. Not just the number 2. Okay, you're not going to get full credit if you just say 2. Okay, it's the line y equals 2. I need to know that you know that you're supposed to produce the equation of a line, so y equals 2. Slant asymptote in this case is none because you never have a slant asymptote if you have a horizontal asymptote. Number 2. Here we are given a quadratic function. Does the graph of the parabola open upward or downward? Well, of course, it is upward because the lead coefficient is 1. It's 1x squared, and that's positive. So 1 positive, so upward. If it were a negative lead coefficient, the parabola would open downward. Find the vertex of the parabola. Well, since the form that we have is ax squared plus bx plus c equals 0, or equals y, that's the form of the quadratic function that we have, not the vertex form, but the standard form. We're going to use the vertex formula, which is minus b over 2a, and in the book they always say f of minus b over 2a. In other words, to get the second coordinate, plug it in, whatever minus b over 2a is. Well, let's see. A is 1. That's an equal sign. B is negative 16. C is 55. Okay. And minus b over 2a is minus negative 16 minus negative 16 over 2 times 1. That's a 1. Which is 16 over 2, which is 8. So the vertex of the parabola is the point 8 something. Eight what? Well, we plug it in. Okay, so 8 squared minus 16 times 8 plus 55. The vertex is the point 8 64 minus 144 Is that right? No. Sixteen times 8, that's 80 plus 48, 128. Plus 55. The vertex is the point 8. Negative 64 plus 55, or negative 9. Okay, so 8, negative 9, that is the equation of the, or not the equation, the coordinates of the vertex. Now, I was about to define vertex for you, but the next question does that. In fact, for that reason, it's kind of a stupid question. Identify the maximum or minimum point. Well, that's the very definition of the vertex. So, well, it's 8, negative 9. Okay, more questions about f. And remember, the vertex is 8, negative 9. And almost all the questions in this sort of ax squared plus bx plus c problem go on the fact of what the vertex is, 8, negative 9 in this case. Okay, so remember that we've got vertex 8, negative 9. Identify the maximum or minimum value of the function. Now that is a meaningful question. And so what are they really saying? What they're really saying without saying it is y value. Y value. Okay? So negative 9. Okay? We probably should say whether it's a min or a max. Well, we said that this parabola is downward opening. Whoops. And so 8, negative 9, or it's upward opening. Upward opening. 8, negative 9, so, you know, it's a parabola, kind of like that, maybe. And so negative 9, that's as low as it goes. Okay, that's the minimum value of the function. Okay. Identify the x-intercepts. Well, that's easy. The intercept problem, to find the x-intercept, to find the y-intercept, you set x equal to 0, solve for y. To find the x-intercept, you set y equal to 0, solve for x. Okay? So we're going to set x squared minus 16x plus 55 equal to 0. And we'll solve it by whatever means necessary. Now, we have two main ways that we go about this. We try to factor it if we can. We look for factorization, which isn't too ridiculously hard to get. And if we have too much trouble with it, we just go right to the quadratic formula, which always works. Okay. Now, I think this is going to factor as x minus 6, x minus 11. So 0 equals, x minus 5, x minus 11. And by the same zero product property, if two things multiply together to make 0, one of them has to be 0, x equals 5, or x equals 11. So the x-intercepts are the points 5, 0, 11, 0. So we'll circle that. Looks like those are the kinds of points that we would have for our graph. Identify the y-intercept. Well, the y-intercept, set x equal to 0, solve for y. That's the easy problem, because the y-intercept is always just f of 0. f of 0. Well, that's 0 squared minus 16 times 0 plus 55. It's just 55. It's just this constant right here, which it always is if you have a polynomial function which is expanded. So the y-intercept is the point 0, 55. 0, 55. Now we're going to graph this thing in the next slide, and of course the point of these intercepts is to have points for the graph, and of course we have the vertex also, 8, negative 9, and the graph will be determined, a parabola is determined by these points. And so with the x-intercepts 5 and 11, let's start putting a graph together. Hopefully one that looks better than the one on this slide. Okay, so notice how 5, 0 is an x-intercept and 11, 0 is an x-intercept. We could have gotten the x-coordinate of the vertex just from this because of the symmetry of the parabola. A parabola is always symmetric about its axis of symmetry. And so we're kind of doing the next problem, the one below, when I do this, but we could have known that the vertex would be the point 8 something just from that. Of course we know it's 8, negative 9, and we know the y-intercept is way up here at 55. So right there we have a parabola, And to get credit on my exam, you either have to show all stages of transformation, or you have to give me 3 points with exact coordinates. Here I've given 4 points with exact coordinates. I have not listed these 0 coordinates. Obviously, if the point is on the x-axis, the second coordinate of the point with first coordinate 11 is 0. The first coordinate of the point with second coordinate 55 is 0. Axis of symmetry, we want its equation. Well, we have the axis of symmetry here in this vertical dotted line, and it is the line x equals 8. So we could have a formula an axis of symmetry formula. The axis of symmetry, of course, is always, put it here in the margin, the line x equals, because it's a vertical line, so it always will have this form of equation, x equals just a number, and the number is minus b over 2a. The domain, well, for any quadratic function, any one at all, that is a second degree function. In fact, for any polynomial function, the domain in interval notation is always just negative infinity to infinity. Automatically. The range, though, that's a whole other issue. Now, when we have a graph and we're trying to find the domain and range, what we like to do is draw a box around the graph. But these arrows, they go infinitely. Like this one here goes infinitely up and to the right. The other arrow goes infinitely up and to the left. So the arrow goes infinitely to the left and infinitely to the right. So we can't draw a left edge of the box or a right edge of the box or even a top of the box, but we can draw the bottom of the box. Well, that's going to help us with the range, because that means that the set of y values, that's what the range is, right? The set of y values. Set of y values, known as the range, is the set of all numbers -9 and up. In other words, in interval notation, the closed interval, -9 to infinity. Number 3. Here we're graphing a function which has a decimal and negative lead coefficient. And it's in factored form. So here, let's think about the x-intercepts. Okay. Usually we start with vertex. Well, this isn't going to have a vertex. It's not even quadratic. This graph is not even close to being a parabola. So we've got a polynomial function in factored form. Actually, it's 6th degree, 2 plus 3 plus 1. But let's start with x-intercepts. Okay, so we're going to start with x-intercepts. Set y equal to 0, solve for x. Well, where is the y? There's the y right there, f of x. That's the y. Y is always f of x. F of x is always y in college algebra. So negative, so we're going to set that equal to 0. So 0 equals negative 1.5 x squared times the cube of x minus 2 times the first power of x plus 1. Okay. Now, if you have, say, 3 things that multiply together to make 0, one of them has to be 0. Either negative 1.5x squared equals 0, or x squared equals 0, or the cube of x minus 2 equals 0. What we're doing here, we're going to be proving the factor theorem, or x plus 1 equals 0. Okay. Well, the first equation is actually the same thing. Whoops. First equation is actually the same thing as the third. I'm sorry, what did I do? Oh, okay. Actually, I was like talking about something else, so I wrote the wrong thing. You're probably wondering why I wrote negative 1.5x squared 0 or x squared equals 0. Let's break it into 4 things. Okay, if 4 things multiply together to make 0, we'll clean up this equal sign too. It's just ugly. If 4 things multiply together to make 0, then one of the 4 things has to equal 0. I'll also supply the missing equal sign in the third equation here. Okay. Either negative 1.5 equals 0, which is ridiculous. Okay, there's not going to be anything, come of that. X squared equals 0. Take a square to both sides. One side is plus or minus. X equals plus or minus the square root of 0. X equals 0. Okay, so 0 is a 0, an x-intercept. In the third equation, well, let's get a different color going here. I guess we'll take a cube root of both sides. Cube root, and x minus 2 equals 0. Add 2 to both sides and x equals 2. We're getting points on the graph. That's the goal here. And fourthly, Subtract 1 from both sides. Subtract 1, subtract 1. X equals -1. Okay, so that when we go to make a graph, we're going to have an advantage here of having all the x-intercepts. So there's an x-intercept at 0, in other words at the origin, which also tells us what the y-intercept is. At 2, there's an x-intercept, and at -1, there's an x-intercept. So that's 2, that's -1. Okay. Now, notice the evenness or oddness of the degrees of each of the factors which give rise to these x-intercepts. Okay. The 2 is obviously even. The 3 is odd. The 1 is odd. And remember how the evenness or oddness of the multiplicities tell you whether the graph crosses or merely touches the x-axis there. Now, it also is going to help us to know the end behavior of this function, the graph of this function. Okay. Now, 2 plus 3 plus 1 equals 6. That's the entire degree. If we multiplied everything out, it would be, if we multiplied everything in f, all the factors out, it would be -1.5 x to the 6th plus some other stuff. Okay, so end behavior is okay, we got a 6th degree function, and it's also important that that's even degree. We have negative lead coefficient, negative lead coefficient. Those two things together tell us that the end behavior of this graph is going to be like this. It's going to come in from below and leave below. Knowing that is going to help us put together this graph. Okay. Those things combined with the fact that because of the evenness of the multiplicity of this 0, that we got from the x squared. In other words, the 0 which is 0. In other words, the one at the origin. Its even multiplicity means that the graph there is going to touch and not cross. Okay. So let's keep all that in mind and make a graph. Now, we said the end behavior tells us that the graph is going to come in from below. Okay. Now, we have the 3 points required for credit. What we don't necessarily know, and what's kind of interesting, is a maximum value of this function. Okay. How high does it go? Well, short of calculus, we don't really have an answer to that. And so I'll just draw something which is reasonable, but which would, give you full credit on this exam. Okay, so come in from below, and then at -1, the multiplicity is odd. It's going to cross there and then go above the x-axis. So come in from below, go above, come back down, but then at 0, we have an even multiplicity there. It's going to touch and not cross. Okay? It's going to go back above, and it's actually going to do something interesting here, and we're not really sure what until we, get some more points and look at a graph. But I'll just make it probably, maybe it goes above like this, and then blips again, because it's 6th degree. Wouldn't do that if it were just 4th degree. But then at 2, we've got another 0 of odd multiplicity.
Given this rational function,
and so
identify the
graph
vertical
is going
asymptote.
to cross. So that is something like the graph of f. Okay,
we're already half hour into this, so I'm going to try to be close enough
succinct
for full credit.
Vertical asymptote,
Because
you've given me 3 points with exact
given by
coordinates.
zeros
You
to
have
the
correct
denominator
and behavior. Set x minus 2
you're
equals
touching
0.
the x-axis where you're supposed
X
to, and
equals
crossing
2 is
where
the
you're
equation of
supposed
the
to.
vertical asymptote. I gave you a lot of theory in the first 3 problems that can be applied to later problems. Horizontal or slant asymptote. And again, separate problems, completely separate. Well, again, the degree of the top is the same as the degree of the bottom. They're both 1. Degree of the top, if I may use t for top as a subscript, equals degree of the bottom. The line y equals ratio of the lead coefficients, so 3/1. Y equals 3 is the equation of the horizontal asymptote. Therefore, there is no slant asymptote. Graph the function. Well, first thing we always want to do for a rational function is to establish the asymptotes. Now, for the previous problem, number 3, couldn't do that because there is no asymptote. Okay, it's a polynomial function. But this is a rational function, and it has asymptotes. The line x equals 2, vertical line 2 units to the right of the y-axis is a vertical asymptote. And the line y equals 3, okay, so 1, 2, the line x equals 2. And 1, 2, 3, the line y equals 3, a horizontal line 3 units above the x-axis, that is a horizontal asymptote. The graph must approach both of those. Now it's tempting just to get some points, throw some points on there, and that's it. I wish I could just say that. Okay, let's make a big old XY chart and get enough points, and we actually would get something that would look pretty good. And as an instructor grading, I would have a tough time, finding a lot of fault with this if you did enough correct points and plotted them and had the resulting curves approach the asymptotes. But it is kind of good to know where, if anywhere, the graph crosses its horizontal asymptote. So let's set 3 equal to, right, because 3, that's the equation of the horizontal asymptote, or the y equals 3 is the equation of the horizontal asymptote. Let's see if we can get anything out of this. Okay, 3x plus 6 all over x minus 2. And solve for x if we can, because then we'll really get a good graph. Okay, so we're going to multiply both sides by x minus 2. X minus 2 x, that's an x, minus 2 okay, so that x minus 2 is of course over 1. Everything is itself over 1. So we can cancel. And we get the quantity x minus 2. I'll rewrite it because it looks so bad. X minus 2 times the 3 equals 3x plus 6. Okay. Well, we can see there's not going to be a solution to this. Distribute the 3. 3x minus 6. 3x minus 6 is never equal to 3x plus 6. You know, we could subtract 3x from both sides to get negative 6 equal to 6. And that's not true. And so there is no point of intersection between the graph and its horizontal asymptote, which sometimes happens. Okay, so no point of intersection. Intersection. Okay. Okay, so let's just get some nice x and y values like -1, 0, 1, not 2. X is never 2. That's why there's a vertical asymptote there, but let's try 3. Okay. Let's start at the bottom. When x is 3, y is 3 times 3 plus 6 all over 3 minus 2, which is 3 times 9 all over 1, which is 27. So the point 327 is on the graph. So the graph is way up here. I mean, it's like way up here, really, 327. Okay. But that's enough to know that since the graph must approach a vertical asymptote and a horizontal asymptote, we're going to have a branch up here like this for this graph. Okay, that's ugly. let's see, let's try blue. Okay. Let's see. When x is -1, we have 3 over -3, which is -1. So there's a point -1, -1 on this graph. Okay. A point 0, let's see, 6 over -2, right? You can cover up the 3x and the x in f of x here, and it just ends up being 6 over -2, which is -3. So -3 is the y-intercept, and we know how this thing's going to go. The point 1, let's see, when x is 1, what do we have? 9 over -1, so that's -9. That's another point way down here. And so we're going to get a piece of the graph over here. There is an x-intercept at -2. We might have put that in there, x equals -2, because when x is -2, the top is 3 times -2 plus 6, which is -6 plus 6, which is 0. That's an x-intercept. 5 determines the center and radius of the circle.
Okay.
But we, given by this equation in general form, of plenty of values to satisfy old Jackson, we have to get, in order to do that, what we need is standard form. There's a graph of the equation of a circle. Standard form, which is the square of x minus h plus the square of y minus k equals r squared. Okay, that's the equation of a circle with center hk and radius r. So going after that form, that standard form, from this general form, first thing I'm going to do is switch these two terms here. So x squared plus 8x. We're going to have to add something to that to complete a square, because here we've got a completed square, right? The perfect square of x minus h. And if you remember your factoring forms, the square of x minus h is x squared minus 2xh plus h squared. So we're going to have to make a perfect square trinomial out of x squared plus 8x plus something. And we're going to complete the square also with the y's. So y squared minus 14y. Then we've got this 56. But because of the r squared in the form that we're going after, that 56 is going to end up on the right side. So subtract 56 from both sides. We're also going to have to add a constant to complete the square in y. Subtract 56. Subtract 56. Now, to complete the square, the move that you have to make is, okay, to complete the square, the move that you have to make is to x squared plus bx add the square of b over 2. The square of b over 2. Okay. Well, b is 8 right now. Right? That's x squared plus bx right there, with b equal to 8. Okay. Well, the square of b over 2 is the square of 8 over 2, which is 4 squared, which is 16. And so we're going to add 16 to both sides. So x squared plus 8x plus 16. Also add 16 on the left. Plus y squared minus 14y plus whatever we have to add to complete that square equals negative 56 plus 16. Now this is a completed square, and you could just factor it, or you could recognize or know that this b over 2 is always that b over 2 is always the number that's going to be inside the parentheses with the x in the factorization. So b over 2, of course, is 8 over 2, which is 4. So that's the number that goes inside the parentheses with the x. So this is the square of x plus 4. And, you know, it's not hard to factor this one and see why that is actually true. X plus 4, and FOIL, and you got the right thing. Well, let's see. We're going to have to add an appropriate number. To complete the square in y, b over 2 is negative 14 over 2. Well, actually, we should add the square of b over 2 to both sides to justify completing the square on the left. The square of b over 2 is the square of negative 14 over 2, which is the square of negative 7, which is positive 49. So we're going to add 49 to both sides. Plus 49. And so now the next step, what do we have? We've got y squared minus 14y plus 49. Well, we know how to get the factorization. The number that's going to go inside the parentheses with the y in the factorization is b over 2. b, the coefficient of the first degree term, is negative 14. Half of that is negative 7. Well, what number do we have on the right here? We got 3 numbers that we have to add together, one of which is negative on the right. Okay, so negative 14, negative 56 plus 16 are negative 40. Add 49, you have 9. Okay? And we now have standard form. We now have the correct form, the form that we need to say what the center is and what the radius is. Comparing this to the standard form, we're going to be able to say what h is and what k is and what r is. H, if you look at the form, h is the number that's subtracted from x. And so h is -4. Okay, h is -4. K is the number that's subtracted from y, which is 7. R is, of course, the square root of r squared. If you compare this equation here to the form, the standard form, you see that r squared is 9. So r, the square root of r squared, is the square root of 9, which is 3. So the answer is the center of the circle is the point -4, 7. And the radius is 3. Okay. Write an equation of the line passing through the points 4, -8, and 2, -3. When you see write an equation of the line,
Okay.
you automatically
so
think
studio here.
Okay. Y minus y1 equals m x minus x1. Okay. And then we'll get an equation of the line. And actually, it doesn't ask for anything more than that. So point-slope form is perfectly good form. Maybe we'll just go with that. Let's see. We need a slope m, which is y2 minus y1 over x2 minus x1 by the slope formula, which is -3 minus -8 over 2 minus 4. That's like -3 plus 8, so 5 over -2. So that's a slope. Okay, that's marginal work here. And the x1, y1 that we used in that formula, well, maybe we'll just use the same one in the point-slope form of the equation of a line. So here's our x1, y1 that we used. We'll use that again. x1 is 4, because we could pick either point, right? We could pick 2, -3. Maybe you like those little tiny numbers better, rather than the convenience of having the same x1, y1 for both the slope formula and the point-slope form of the equation of a line. Just don't mix and match. You got to have the same point. You got to have two coordinates of the same point for the point-slope form. Slope, we said, is -5 over 2. And so a perfectly acceptable answer here is y plus 8 equals -5/2 x minus 4. Students generally feel compelled to put their answer in slope-intercept form, but you don't have to. But of course you would add 8 to both sides and distribute the -5/2 and combine the constants, -8 and the other constant that you got from the distribution, in order to get the slope-intercept form y equals mx plus b. But do memorize this point-slope form of the equation of a line. very important, point slope form. Determine the x and y intercepts of the graph of x equals y squared minus 9. Well, to get the x-intercept, you set y equal to 0 and solve for x. So x equals 0 squared minus 9. X equals negative 9. And so the x-intercept is the point negative 9, 0. Y-intercept. To get the y-intercepts, that are going to be multiple in this problem, you set x equal to 0, solve for y. Set x equal to 0, solve for y. So we will add 9 to both sides. Nine equals y squared. Take a square root of both sides, and it's just 3, right? Wrong. Take a square root of both sides, and remember the square root property from Unit 1. Square root property says that when you take a square root of both sides, one side is plus or minus. So the y-intercepts are the points, 2 points, 0, 3, 0, negative 3. This graph is the graph of a sideways parabola, which is why it's strange in the sense that it has one x-intercept and 2 y-intercepts. It's not the graph of a function. Graph a piecewise defined function. Okay. Well, let's see, this top thing, if we did not consider the piece of the domain, x less than 1, you know, that this graph is just the graph. What did I do? Okay. This is only going to be the graph on the left, and there's going to be a different graph on the right. But if we didn't consider that, y equals negative x minus 1. Okay, y equals negative x minus 1. Y-intercept is negative 1. Slope is negative 1. Slope is negative. It goes downhill. The line goes downhill as we read from left to right. That is the graph of negative x minus 1. Y equals negative x minus 1. And then it's also good to you know, think about the other piece. What does that look like if we're not concerned about, you know, what part of the domain or subset of the domain is it for which this graph holds? Well, square rooting function, hopefully you see that in your mind, going off into the first quadrant with an endpoint at the origin. The replacement of x with x minus 1 means there's a right shift 1 unit. So here's that graph. Okay. Well, we're going to put them together. For the top one, that's just what we're going to have on the left. For the bottom one, that's all we're going to have on the right, which is good because it only has a right side. Okay. Okay. Okay, so let's do that part first. Starts at 1. goes off like that. Okay. The other one, coincidentally, no pun intended, arrives at the point 1, 0. Wrong. Sorry, let me fix that top graph. I said x-intercept -1, and then made a graph that has x-intercept at 1. I was kind of focused on the downhill, but here's that graph. Now, and we have to know where this, what happens at 1. I mean, the whole thing would be this. Okay, so it's coming down like this, but then what's the y value? Where is the thing in the vertical when x is equal to 1? Well, if you put 1 in for x, you get -1 minus 1, which is -2. So it ends at the point 1, -2. However, that point's not on the graph, so we put an open circle there. This is a function, and so, x does not repeat. When x is 1, f of x is 0. We know that that's where the closed circle is because we've got the little equal sign underneath the inequality symbol for the bottom rule, okay? Not the top rule. For the square root of x minus 1, not the negative x minus 1. Graph shows U.S. expenditures in millions of dollars for national parks for selected years. Okay, so and all those numbers are in thousands, so this 3,000 here represents $3,000 million. In other words, $3 billion. In the graph, x equals 0 represents the year 2000. Okay, so that's the year 2000. That's the year 2002. That's the year the Texans came into existence. The year 2004. Most of you were too young to realize that, probably. 2006, 2008 to 2010. Use the points 0, 1833 and 8, 2614 to find a linear function representing the expenditures E of x for national parks x years since 2000. Round the slope to the nearest whole unit. Okay, so we got these points, and it's just the old problem of find the equation of the line passing through 2 points. Now I said the words, find the equation of the line. Does something ring a bell? I said when I say the words, or when you read the words, find or write the equation of the line, you always think y minus y1 equals mx minus x1, the point slope form. Okay. Now, slope intercept form is y equals mx plus b. And we wouldn't even worry about that yet, except for the fact that they actually did give us the y-intercept, the 0.0 something. So because of that advantage, we'll just start right with the y equals mx plus b. Try to figure out the m, and we're given the b. The b is 1833. That's the y-intercept. So let's see. It's x and e of x. X is the number of years since 2000. And e of x, okay, 1833, where we're keeping everything in millions for e of x. Now I wrote y, but it's e of x. E of X. Expenditures. Okay. Now all we need is M, and we've got an equation. They say to round the slope to the nearest whole unit. So we're going to use a slope formula. y2 minus y1 over x2 minus x1. And that's 2614 minus 1833 over 8 minus 0. Now the top there, let's see, if it were 18, well, let's see, if it were 2633, in other words, if it were 19 more, then it would be 800. But it's 19 less than that. So it's 781. And the bottom is 8. 781 over 8. Trying not to use a calculator here. Let's see. That now, if it were 800 over 8, it would be 100. If it were 792 over 8, then it'd be 99. If it were 784 over 8, then it would be 98, and that's the slope to the nearest whole unit. So approximately equal to 98. Okay, so E of X equals 98, approximately 98x plus 1833. If the linear trend continue, use the model from Part A to estimate the expenditures for U.S. national parks for the year 2015. Round to the nearest million. Well, when the year is 2015, what is X? Well, X is 15, right? Because X is the number of years since 2000. Okay. Well, what's E of 15? That'll give us the expenditures in this year. E of 15 equals 98 times 15 plus 1833, which is, well, let's see, if it were 100 times 15, then it would be 1500. If it were 99 times 15, then it would be 15 less than that, which is 1485. 15 less than that, or 1470. 1470 plus 1833, 3303, 3303, okay, and it's 3303 million. Now they say round to the nearest million, as if, you know, it were possible to do anything else. We already did our rounding in Part A. So we estimate expended. We always answer a word problem in words, right? Because we want credit. Expenditures to be $3,303,000,000 in 2015. Find the x-intercepts. Find the y-intercept. Find the vertex of the parabola. Okay. Well, to find the x-intercepts, we set y equal to 0, solve for x. This time, not as straightforward. And let's see, does it factor? Let's see, if we had a 2x and an x, we'd have to have a 1 and a 1. It's not going to factor. X equals, so we go right to the quadratic formula. X equals minus b plus or minus square root b squared minus 4ac all over 2a, which is 6 plus or minus square root 36 minus 8 all over 4, which is 6 plus or minus square root of 28 square root 28 all over 4. Square root of 28 is the square root of 4 times 7, which is the square root of 4 times the square root of 7, which is 2 times the square root of 7. Okay, so this is 6 over 4, okay, putting it the way Connect Math would like it, plus or minus 2 root 7 over 4. And these fractions reduce to 3 over 2 plus or minus root 7 over 2. And the x-intercepts are the points 3/2 plus root 7 over 2, 0, 3/2 minus root 7 over 2, 0. Two irrational numbers for the x-intercepts. Now the y-intercept is easy, it's just 1. 0, 1, because it's f of 0, and 0 blows up all the terms except the constant, which is 1. Making a mess of that. Vertex of the parabola well, what's the formula for the vertex of the parabola? If what you have is ax squared plus bx plus c form. Okay, so it's going to be minus b over 2, plug it in. Minus b over 2, minus b over 2a. A formula not to be confused with the square of b over 2. Minus b over 2a, plug it in. Minus b over 2a, f of minus b over 2a. So minus b over 2a something, which is minus negative 6 over 2 times 2. Something. Which is let's which is 6 over 4 something. Which is 3 over 2, plug it in. So 2 times the square of 3 over 2. Remember, the squaring has to happen before the multiplication. Minus 6 times 3 halves. Plus 1. Okay, so the first coordinate is 3 halves and the second coordinate is whatever all that is. Which is 3 halves just to emphasize the squaring before the square rooting. Okay, what are we squaring? We're squaring 3 halves. So 3 over 2 times 3 over 2. Multiply across. That's 9 over 4. So 2 times 9/4. And let's see, that's 6 is itself over 1. It'll cancel with the 2, leaving a factor of 3, so minus 9 plus 1. Now I'm going to, whoops. Okay, well let's take another step. 3 halves. The 2 and the 4 cancel, leaving a factor of 2 in the denominator. So 9 halves. Minus 8 plus 1, so minus 8. Minus 9 plus 1, so minus 8. And combining, adding the fractions, 9 halves minus 8 is 9 halves minus 16 halves, which is negative 7 halves. So 3 halves, negative 7 halves, that is your vertex. And to circle it without making a mess, well, now we'll go back to the red. Solve a polynomial inequality. Okay, well, looks like it factors. So what do we do when we have 4 terms and we try to factor? Well, we split the thing down the middle, factor the first pair of terms and factor the second pair of terms, and then factor the result, hopefully. Well, let's see. We pull out a negative x squared, because negative x squared is the greatest common factor of negative x cubed and negative 5x squared. And that's going to leave x plus 5. Well, is x plus 5 also a factor of the second pair of terms? Well, yes, if you pull out a 4. Then the factorization of the result, one of the factors is x plus 5. Okay. And we get that, right? You got two addends now, and they both have x plus 5 in them. So x plus 5 is going to appear as one factor in the factorization. What's the other factor? Other factor is negative x squared plus 4. Okay. Now, that is the same thing as 4 minus x squared. And we remember that all this is less than 0. Okay. Now, we're going to solve the auxiliary equation in order to know where this is equal to 0, in order to know what are the endpoints of the intervals of solutions to this inequality. Because we know that this inequality, its solutions, they're going to be intervals of x values. It's not just going to be like a number, right? It's not going to be like, 10 or something. It's going to be whole intervals of x values for your solutions. Okay, so let's solve the result of related equation. 4 minus x squared, x plus 5 equals 0. Equals 0. Well, this is 2 minus x, 2 plus x, x plus 5 equals 0. And setting each factor equal to 0, we get, for our important numbers, as I like to call them, because the term critical numbers is so abused, as is the term abused itself. Important numbers -2, -2, -5. Okay. So, let's see. We could, oh, it's so ugly. Make a number line. I think I'm going to do the rest of this in a different video, maybe on a different night. Okay, so we can make a number line for these important numbers. We'll just put them, in convenient places. They don't have to be to scale. -5, -2, 2. And so we're concerned about actually 4 intervals. The interval to the left of -5, the interval between -5 and -2, the interval between -2 and 2, and the interval to the right of 2. Okay. So let's see. I'm going to make a chart. Okay, so our intervals, and some subset of these intervals is going to be the solution set. So interval how did that look like that? Okay. So we're going to write down those intervals exactly the way I just said them. And then test points in each interval to know which intervals are going to be part of the solution set. Then, so then we're going to need test points. Test points. Test point C, okay? And then we're going to get f of C, where f is this left-hand side here. We'll call that f of x. Test point C f of C and then when we know the sign, we'll know whether it is less than 0, as the right-hand side of the inequality says, or not. Okay, and so if we know the sign, then we'll know which are the winning intervals, and we'll just select them, and we'll have our answer. So sign. So the first interval is the interval of all the numbers to the left of -5. -infinity to -5. Then all the numbers between -5 and -2. All the numbers between -2 and 2. All the numbers to the right of 2. Test points, these are just arbitrarily chosen, just any number in each interval, and that's going to tell us how the whole interval is going to go. I'm going to pick -6, -3. I always pick 0 if possible because it's the easiest number to work with, and 3. Now f of c, and I'm going to use the factored form for f of x, okay? So I'm going to take this form right here, and that's going to make this easier. Okay, so f of x equals 2 minus x, 2 plus x. Getting late here. Two plus x, x plus 5. That's f of x. Okay. Now let's start with the 3 and go to the left from there. Okay. F of c. Okay. So f of 3. Now, f of 3 is 2 minus 3, 2 plus 3, 3 plus 5. And we could figure out all that. Negative 1 times 5 times 8, negative 40. But we didn't have to figure out the number. All we really needed to know was the sign. Okay, so the sign of all that is negative. The sign of all that is negative. And so actually, you only need to know the signs of each factor here, because if you know the sign of each factor, then you know the sign of the whole thing. The sign of the whole thing will be positive if you have an even number of negative factors, and negative if you have an odd number of negative factors. Okay. Now for the 0, okay, for the 0 you put a 0 in there, and in there, and in there, and what do you have? You have 2 minus 0, so a positive factor, another positive factor, another positive factor. All the factors are positive. The product is positive. When x is negative 3, you're going to have a 2 minus negative 3, which is like 2 plus 3, so that's positive. When x is negative 3, you have a positive first factor, a negative second factor, and a positive third factor. The product of all that is negative because you have an odd number of negatives, namely 1. And so we have a situation that's not unusual, oscillating signs, negative to positive to negative, and if this holds, this one here is going to be positive. Let's see, is it for x equals negative 6? Well, let's see, we've got a positive times a negative times another negative. Yep, 2 negatives. Negative times a negative is a positive. Positive times a positive is a positive. So, the winning intervals. And they're winning intervals only because, let's see, they're winning intervals only because the inequality symbol we were given at the very beginning for this problem happened to be a less than. That makes these two negatives here the winning intervals. And the answer then is the union of the open interval, negative 5 to negative 2, the union of that with the open interval 2 to infinity. Okay. Now, normally, now I'll say that and we're done, and I hope you understand that, and I don't want to confuse you with saying anything further. Okay, so there it is. There's the answer.